So, hello everyone, I am Dr. Sachidanand Sen and working as Associate Professor in the Department of Electrical and Electronics Engineering under School of Engineering, SR University. And today we are continuing with the subject of battery management systems, and the second lecture we are going to learn about the grid scale energy storage. So, what do you mean by the grid scale energy storage? So in this, what we are going to see about what is the purpose of grid scale energy storage, why all the energy storage facilities that we are having, like different types of batteries, okay, pumped hydro is there, then flywheel is there, why some of them are suitable for grid scale, whereas some of them are not suitable for grid scale, rather they can be considered for the application of electric vehicles. So first of all, let us learn about the definition of grid scale energy storage. So it refers to a large capacity systems in the range of megawatt or even gigawatt range that stores electricity for large use, enabling efficient and reliable power system operation. So like in the wind farms, all solar farms, all of these renewable energy integration that we are doing in megawatt range. Okay, so in that definitely a few kilowatts of batteries will not be sufficient enough to act as a energy buffer. So definitely the quantity of energy storage or the ability to store the large amount of energy that need to be facilitated. So that the word grid scale is nothing but large scale, because grid is considered to be in the megawatt or gigawatt range. So that is the grid scale energy storage. So why it is important? It helps in balancing the supply and demand in real time. So it helps in balancing the supply and demand in real time and integrating intermittent renewable sources. Just now I mentioned it helps to integrate the intermittent renewable sources. Why these are called intermittent renewable sources? Means whenever surplus generation will be there, suppose it's a summer daytime, so definitely more electricity will be produced by solar panels. Similarly, suppose it's a windy day or windy night, so wind speed is above the average speed, so definitely power generated by wind will be also more than the average output. So in that case, we are going to have more energy output. So during surplus generation, we can store the excess energy, and during the deficient generation, definitely we have to use that stored energy back from the energy sources or energy storage units. So this will help to maintain the supply and demand. Okay, maintaining a supply and demand means whatever is the load requirement, definitely that much level of generation should be always there, so that the voltage and frequency of the grid will not deviate from their nominal rating. So in India, all of us are aware that 50 Hz is the required frequency. Similarly, the single phase household supply, we are expecting the RMS value of the voltage to be around 230 volts. So that need to be maintained by proper supply and demand balancing. Then providing grid stability and resilience. So that the term grid stability represents that only, whether the frequency and voltage are within the nominal range, they are not deviating from the said tolerance band or like that. And even if it is some loads are changing, some faults are occurring, it is resilient. It is again coming back to its initial position. So reducing the dependence or reliance on fossil fuel based peaker plants. Peaker plants means the power plants or the generation stations which supply for the peak loads. So generally that hydropower plants, they will be, suppose a small scale hydropower plant, sudden requirement of load is there. So definitely they will turn on something which will be quickly able to produce the electricity. Suppose renewables are not available or energy battery from the energy, battery is also not available. So definitely a short term power peaker can be used. So such are called peaker power plants. So definitely if we are considering gas turbine, these are fossil fuel based, definitely it will consume more, mm, or it will burn more carbon dioxide and emissions will be created. So these are the problems if we are considering the uh, fossil fuel based peak power plant. So generally we will go for either hydro or some form of large scale dispatchable battery units. Okay. Now the context in this will be like by 2030 we are expected, like global demand for grid storage is expected to exceed around 2000 gigawatt hours, driven by decarbonization goals and renewable integration. Now this much of energy is required, and decarbonization goal, like recently in the Paris agreement also they have decided that each and every developed nation will gradually bring down their dependency on energy generation from the fuels, fossil fuels. Okay, so like carbon based, like coal, then crude oil. From there they need to migrate towards the greener renewable sources like solar, wind. In that, electric vehicle is also one of the important component, because electric vehicle where the battery are mainly preferred, in that we are going to add more value in terms of sustainability, and environmental impact will be less. Now, this is one example, like you can see here, some power grid is there, households or residential loads are connected. In that power grid, we are having industrial loads also integrated with that one. In this power grid itself, we are having renewable energy sources, and it is directly, it can supply to the power grid, or it can store, it can supply the surplus generation to the energy storage unit. Similarly, we are having conventional power sources, mostly thermal power plants. Still in India, we are depending upon the thermal power plant up to 60, more than 60%. Still we are more depending upon the thermal power plant by more than 60% of the energy. So this shows here the dynamics of the energy storage. So it will, whenever, mostly it will try to capture the energy generated by the renewable sources. And when this will be feeding the energy storage, whenever the renewable sources output is more than the load present in the power grid. And these are power plants which are almost constant demand. Most of them are acting as a base load. So they will be supplying the base loads. Okay, and if the generation from the renewables is its magnitude is somewhat comparable to the magnitude of the power plant, then only it will be a grid scale energy storage will be able to contribute in a more optimal way, or it can make the renewable energy sources work in a better way if the percentage of penetration of renewable sources is almost comparable to the percentage involvement of the power plants. Okay. Now this diagram also depicts somewhat similar patterns. So here you can see x-axis represents time of the day, like 00 is the midnight, 6 o'clock is the morning hour, afternoon, then evening 6 o'clock, then again 24 hours. So this represents a 24-hour time of the day representation. And here you can see the power. Okay, so load demand is represented by red color. Here you can see the during midnight to morning 6 o'clock. Generally, this green line is suppose representing the average load. So this will be lower than the average. And here, and whatever energy is stored, suppose energy is generated mostly during night time, means all the energy is generated from the wind energy. If sunlight is not there, means solar panel output will be 0. So this wind energy will be used to store the energy of the batteries. Okay. During suppose morning time, when the loads are increasing, because as the people get up in the morning, okay, offices will be starting, industries will be running, so load will be generally gradually increasing as the time passes, and around mid of the day or 10 to 4 it will be at the peak value, around the maximum value, and again it will slightly dip down gradually. Although it's approximately represent, because maximum load is generally happening around the evening time. In Indian cities, most of the mm, peak will come around evening time, 6 to 8 or 8:30, like that. Okay, so this is just a rough estimation of the load demand, load profile, you can say. So this is what load profile looks like. Similarly, after 6 o'clock, again the uh, load is suppose shown here to be decreasing, and during that time the energy storage will be gradually increasing. So this is how it works, and here you can see during lower load demand, storage unit was positive, it was charging mode, and when the load was more, and you can see the energy stored in the batteries were consumed, released, okay, into the power grid. So this was the discharging zone. So some portion of any energy storage throughout the day, it will be charging mode. Whenever the load is less compared to the generation or outcome, so it will be charging. And the reverse thing, whenever the load is more than the generation, definitely it will be in the discharging mode, where the energy will be supposed to flow from the stored units to the loads or the power grid. So this is what the energy flow to and from the storage. Okay. So now come to the services and applications of grid scale energy storage. So where this grid scale energy storage is used, okay, that part we will see. What are the services it can provide, what are the different applications that it is having. Okay, energy arbitrage. Arbitrage means something you are purchasing, suppose at cheaper, you are selling it as a higher price. Okay, similarly something you are storing when surplus is there, and you are using it afterwards when there is a deficiency. So such things are called arbitrage, energy arbitrage, or it is another word, in a simple word it can be also said as load shifting. So here what happens, it stores the excess electricity during the low demand or off peak. Okay, when the demand is lesser, already I have shown you in this graph, when the demand is less, energy will be stored. Okay, so stores excess electricity during low demand or off peak hours, and releases during high demand peak hours, like in the middle between the morning to the evening time. Okay, so what are the examples? Like solar energy stored in the afternoon, okay, used in the evening. Okay, so during afternoon time what happens, the sun is at its peak, so maximum amount of energy is generated by the solar panel. So if the storage devices are capable to capture that one, or are able to store that generated output from the solar panels, during the evening time when the sunlight is gone, the storage devices will be able to sustain the load for a certain duration of time or certain percentage of the given load. So that mechanism is called the energy arbitrage. Next service that it can provide is grid stabilization. Okay, already mentioned the benefits of equal demand and supply. So it will help to stabilize the frequency, voltage support. It will help to for frequency regulation, voltage support, inertia provision. So voltage and frequency support I already mentioned, they need to be operated within the given range. Like for voltage it is plus minus 10%. Okay, similarly for frequency it is around plus minus 3%, or plus maximum extent it will go up to plus minus 6%. Okay, so of the 50 hertz. Okay, so like that you have to consider that one. Similarly, inertia provision means, like most of us are knowing, there are thermal power plants where the large generators are rotating. So large generators are having that momentum, that rotational motion is there. Okay, moment of inertia is there. Okay, whereas if we are connecting the renewable sources like wind turbines and solar panels, it does not have large size rotating masses. Okay, so because of lack of that large size rotational masses, what happens? The droop control cannot be implemented in a proper way. Droop control is nothing but relationship between real power and frequency. it is expected as the real power demand is increasing, the frequency will gradually drop. So that kind of inertial effect has to be incorporated with the help of voltage source inverter, or you can say the converters which we are using to integrate the solar panels or the wind turbines. They will have to create some form of virtual inertia, that is called the inertia provision, that has to be managed by the controllers of the converters or energy management systems. Okay, then fast response technologies, as already mentioned, grid stability means within fraction of seconds it should be able to connect the generators, or it should be able to disconnect the loads depending upon the requirement. So fast response means batteries, flywheels, these are the key players which will be able to support these roles. Okay, means quickly they will be able to connect, quickly they will be able to disconnect. So that system is not suitable for other types of energy sources. Now in a renewable integration, already mentioned that smoothing variability of solar and wind. It will help in smoothing the variability like intermittency or uncertainty, because as the fluctuations throughout the day is there, cloudy day is there or rainy day is there, so output by the solar panels will be degraded. It will be continuously changing throughout the day. Similarly, wind definitely is more suitable example, because throughout the day wind speed is not constant. It will be sometimes higher, sometimes it will be lower, sometimes it will be zero. So nil speed means there won't be any wind power output. Okay, so farming renewable power output to make it dispatchable. Okay, so with the help of grid scale energy storage only, we are able to bring in some form of smoothing effect in the intermittent renewable energy sources. Intermittent in the sense the highly fluctuating, uncertain output that we are getting from the solar as well as the wind turbines. Then backup and resilience. So what is the meaning of backup and resilience? So because battery are capable to store surplus energy when all the energy sources or renewables, it can be thermal, everything is gone. So even if we are having a battery, we can use that one to turn on or bringing some emergency output. Like in hospitals, diesel generators were used. Similarly, now battery storage are used. Similarly, in lab we are having computer systems, and computers are directly not connected to the power supply. They are connected through uninterrupted power supply, UPS. Okay, so that is acting as a backup. Okay, at least it will provide you certain duration of time to store something. Okay, so provides emergency backup during outages or some form of disaster is there. Suppose cyclone happened, earthquake happened, if the power plants are not being able to be operated properly, in those scenarios definitely some form of backup or this type of things are required, backup plans. Okay, so grid scale energy storage are considered to be able to provide emergency backup during outages or disasters. So it enhances the microgrid operation. So what is a microgrid? Just briefly I will explain. Microgrid is a single point connection with the main power grid, and this microgrid itself will have its own sources like solar, wind turbine, battery based storage, and some of its loads. Okay, like you can say the university itself. Okay, this university, you can say it is connected to the distribution network at one or two places maximum. Okay, so that one place is called the intersection point is called the point of common coupling. Okay, so it can be isolated, and if the loads within the microgrids are small enough, so the generations or the renewables being installed over the rooftop, like solar panels are there. We don't have any wind turbines because the average speed around this region is not that much that it will be viable or cost effective to install wind turbines. So mostly solar panels are there. So that solar panels will be sufficient enough to maintain the given loads. Okay, so that type of entity which can be isolated and it can be grid connected to operate as a single autonomous entity are called the microgrid systems. Or it will definitely enhance the operation of the microgrid system. So then deferred of grid investment. So if we are considering grid scale energy storage, what happens now? Avoiding upgrading the transmission lines, distribution infrastructure by managing the local supply and demand. So see, this installation of transmission line, it's a long-term project. So at least 3 years, 5 years time it takes. Similarly, installation of thermal power plants, like that gestation period. So the time taken for the power plant to lay the foundation and by the time it is operational, it takes around 3 to 5 years. Okay, depending upon the priority that government is there or the private parties, those who are involved, they are putting in. So minimum 3 to 5 years it will take to make it operational and to supply the generated power. Similarly, it will take some time to install transmission line to create the power corridor so that large size generator outcomes can be extracted and it will be able to be dispatched to the load centers or within the nearby cities. So that type of things, it takes some time. So deferred grid investment. So if we are switching towards the grid scale energy storage, definitely some delay we can make it towards these things. So it will definitely help us to create or manage local supply and demand. Now this diagram also shows the similar thing. So here I will start with the power grid. So here is our reference power grid. It will have definitely multiple sources, and here suppose renewable source we are considering solar. So whenever during daytime solar was there, okay, you can see here just now. So this is daytime, so excess solar is there. So it will help renewable energy sources. Suppose here wind can be also a part, of course. So this will, renewable sources will be used to supply to the grid, and it will also help to charge the storage energy during daytime, like this current position. It is charging. Now as soon as the night happens, okay, power generation will be zero. So during night time, the reservoir battery etc discharges. So this will start to discharge. It will run the electric generator or directly it will be able to supply to the grid. Here you can have a converter also instead of electric generator, because electric generator is used because here we are not just only confined our discussion to batteries. Definitely stored energy can be in different forms that we are going to see in a short while. Okay, so power grid can have also multiple sources, that also I have already mentioned. So this is the charging and discharging cycle of grid scaled energy storage throughout the 24 hours duration. Now come to the different types of energy, grid scale energy storage technology. The first one and the most oldest, you can say, the pumped hydro storage system. So in pumped hydro what happens? So here one higher upper level reservoir will be there where large amount of water will be stored. Okay, that water when it is dispatched, it will pass through the penstock and at the lower end the hydro turbines will be operated and it will be able to rotate and extract the electricity. And that water, run down water, is not allowed to flow into the rivers. It will be again stored at the bottom end. Okay, so and it will be pumped back through the channels again to the upper reservoir from the lower reservoir. So that process accounts for greater than 90% of the global grid scale energy storage capacity. So as I already mentioned, this is one of the oldest technique that we have been using for energy storage. So here you can see greater than 90%. Okay, so it is almost till now highest priority we have given on pumped hydro, because in terms of ratings, because this can also be in the megawatt ranges. Okay, so works by pumping water uphill during low demand and releases it through turbines during peak demands. Okay, so when the water will be pumped during the power demand is less, or we are having sufficient renewable, and to pump back the water uphill to the upper reservoir, we will not depend upon the grid electricity. We will be installing some wind or solar panels near the vicinity of the uh, hydropower plant itself, okay, or pump storage unit itself, okay. So works by pumping water uphill during the low demand and releases it through turbines during the peak demand. So pros, what are the pros? Mature, large capacity, okay, long duration. So this is a very mature technology. More than 100 years we have been using this one. The size of the uh, grid scale or this pumped hydro is in the megawatt range, or in fact it will range up to 50 megawatts, 100 megawatts also possible. Okay, so in that case large capacity is there and long duration. As long as water we can pump back within 24-hour duration, at least 3 to 4, 5 or even 8 hours it can be operated depending upon the water levels in the upper reservoir. Now come to the cons. So what are the disadvantages? So it will definitely geographically limited. We always cannot form this high storage, that reservoir, lower storage, deep reservoir. These are limited. Very hilly areas will be there. Okay, sometimes some construction need to be done. Okay, so these are some region constraint. Okay, geographical limited, long construction time. So here also, as already mentioned, gestation time will be larger, and environmental concerns. So if we are not allowing the water to flow downstream, so whatever is the ecosystem below that one, okay, ecosystem will get hampered. So like river, it will be dried up. Okay, so example can be like Bath County pumped energy storage in US. It is, I think, having the highest ratings, 3 gigawatt. Oh, so this is one of the example. Now the most prominent or the most trending one right now, its contribution is gradually increasing day by day. That is battery based energy storage system. Okay, battery energy storage system. So here mostly we are considering lead acid or lithium ion batteries. So most widely deployed fast response. Although lead acid is more economical, but lithium ion is having better KPIs, better performance indices. So most widely deployed fast response, and it is scalable. So lithium ion batteries will be considered for wide deployment, fast response and large scale integration. So used for frequency regulation and peak saving. Frequency regulation and peak saving already mentioned. Peak saving in the sense when the load is peaking, I will show you the diagram, when the load is peaking, if during that time we are able to supply through the stored energy, what will happen? The power requirement by the peak demand or the power required during that peak demand will be slightly offset, okay, because of the supply provided by the or the support provided by the battery sources. Okay, so that saving is the cutting of the peak load is called saving. So here one example can be like Hornsdale Power Reserve. It is in Australia. It is ranging, its ratings are around 150 megawatts, okay, or 193.5 megawatt hours in Australia. So then flow batteries, so it's a large size vanadium zinc bromine can be used, okay, store energy in liquid electrolytes, okay, ideal for long durations. So these can be useful for long duration energy storages. Long life cycle, easy scalability. Scalability means you can add more and more battery capacities. Ratings can be gradually enhanced. Okay. So what are the pros? Pros means advantages like flexible siting. It does not depend upon any hilly areas. It is not location specific. You can install in hill station, you can install in coastal region, you can install it in desert area. Anywhere it can be suitably installed, and it is modular. small modules can be brought in, interconnected, and you can have a large capacity of the battery based energy storage system. Then cons, in coming to the disadvantages, cost. Of course, battery means it will be manufactured, it will be having some rare earth materials like we have just now seen in the first lecture. So definitely it will have better, it will have some more costly affairs. Okay, cost and raw material sustainability will be the main concerns. Now coming to the other naturally available energy storage facilities like compressed air. Although these are not that much suitable and not that much having large scale magnitude, but also these are coming under the category of energy storage. That's why we are having a brief discussion. So compressed air energy storage. So here what happens, like caves are there, old caves, so where air can be compressed through proper suction mechanism. So this can be like stored air in underground caverns or caves under pressure, released to drive the turbines. Okay, the pros can be large scale potential, long duration storage can be there. It requires suitable geology. Again, it is a location specific. It cannot be installed just like that anywhere. Okay, one example is in Germany, around 290 megawatt is the capacity Huntorf plant. Okay. Similarly, thermal energy storage. Thermal means we are going to utilize the heat energy available from the sunlight. So in that heat energy, what we are doing, used in concentrated solar power plant. So instead of photovoltaic, we are having steel based solar power concentrator. So they will be, when the light will be falling on them, they will be absorbing the heat, and that will be channeled through a pipe system where that pipe will be having some molten salt. So they will be able to retain the heat for a longer duration, and it will be circulated through the channels, and like thermal power plants, it will hit the or it will impede the turbines by through superheaters, and definitely the temperature will be raised around 800, 700, 800 degrees Celsius to generate, to convert the water into the steam and extract the electricity like what happens in the thermal power plant. So stores heat, later converts it to electricity via steam turbines. Okay, so what are the pros? Long duration. Okay, like overnight it can store the heat energy, and during the daytime it will store, and during the night time it will be able to extract the or maintain the thermal energy storage system. So low cost storage. Okay, then cons can be limited to CSPs. Okay, concentrated solar power, low round trip efficiency. Round trip efficiency is less than 50%. Okay. Then one example is there in Morocco. Okay, Nur Quarzazate solar complex. Okay, so this diagram shows a better, or you can say the actual representation. Here you can see again time is divided into 24-hour scale. Okay, wind energy is, suppose these are all other sources, means it can be thermal based, hydro based, all things. Suppose wind energy is contributing like this. You can see during daytime or mostly evening time wind is there. Solar is from the morning 6 o'clock around to up to 5:30 or 6 o'clock. Okay, this is the solar output, and this is the actual representation of load demand. Okay, and as the day grows, the load demand will peak, and in the evening time again it will sustain, and gradually it will fall after 8 o'clock. So this zone where battery, if it is able to during this phase, battery will be able to charge. Okay, because here you can see surplus energy is there. So battery charging zone will be from this moment to this moment. As soon as this is falling, so whatever is the solar, that will be used to supply the load, and remaining will be provided by the battery which was charged during this phase. So like that, a proper daily power demand can be managed. Okay, meeting daily energy demand can be maintained. So this is the role of battery based energy storage for a grid scale. So other types of energy storage units that we are having is flywheels. Flywheel is a large size rotating mass. Okay, generally it is stores the energy in the form of rotational kinetic energy. Okay, So some cylindrical shape will be there and it will be high speed RPM it will be generated. When it will absorb the energy, surplus energy, it will gain the speed. So it will be accelerated to a higher speed. Okay, so when it will be discharged, it will decelerate. Speed will be reduced. Okay, so that is how it operates. So extremely fast response, less than 1 second, long cycle life is there, short duration. Okay, this will be in milliseconds, seconds to millisecond range. Okay, and high cost per kilowatt. It is not that much suitable also. Unnecessarily something is continuously rotating means it is not considered to be energy efficient. So frequency regulations, but for some small scale operations it will be suitable. Then hydrogen energy storage. So recently we are gaining the uh, confidence in hydrogen energy storage because the cost economics are coming in alignment with the required facilities. So electricity is used to get hydrogen from the process of electrolysis. Okay, so electricity will be used to break down of the water and hydrogen can be extracted. That process it's called electrolysis and the equipment is called electrolyzer. Then that hydrogen can be stored inside a tank, okay, which can be moved to other places, transported, and again through the equipment called fuel cells. So that stored hydrogen can be used as a fuel into that fuel cell and it will again give us back the electricity. Okay, so which is stored and can be reconverted via fuel cells or micro turbines. Okay, so what are the advantages of these things? So we will again discuss this hydrogen in more detail. In fact, one lecture we are completely dedicating for hydrogen based energy storage. So here the advantage is seasonal storage. Okay, multi-sector coupling, it will help us in transportation industry. Here the efficiency is less. Okay, European valleys, some examples are there, but still commercialization is not yet been implemented for hydrogen storage. Okay, so this is one of the facility in Beacon Power, New York. Okay, 20 megawatt of flywheel energy. You can see these are the underground rotating bodies will be there. It will be rotating, gaining speed, and it will slow down. So like that, it will be helping to store the energy and disperse the energy as required. Okay. Similarly, this diagram also shows like solar panel is there, wind is connected. So electrolyzer, hydrogen production mainly it is showing. So water is provided, electrolyzer is the device, it will give output as oxygen and hydrogen. Hydrogen will be stored in hydrogen storage. That hydrogen can be again provided as input to the fuel cell and oxygen also need to be provided and it will give you the water and power can be provided as the output. So this combination of electrolyzer, hydrogen tank and fuel cell, this all three can work as if combinedly they are doing the work of a battery. So it will store the energy like in the form of hydrogen using electrolyzer. That again hydrogen can be reused by the fuel cell to again extract the required power. So this is like your charging. This process will be called discharging in case of the battery. So it will be combinedly acting as a battery. Okay, implemented can be, or it can be used as a replacement for a battery. So this diagram shows the working of solar panels. So DC current will be generated, inverters will be there, and here directly we can provide it to the loads, AC loads. And here you can see electrolyzer, hydrogen tank combination is there, fuel cell. Of course, fuel cell will again provide you DC. So DC will be converted into AC, and through that AC loads can be sustained. Okay. So these are also some graphical representation of hydrogen storage facilities. So some case studies and real world projects that are being developed at a prototype stage that we are going to see now. Briefly, I will cover this one. So Hornsdale Power Reserve in Australia, suppose world's largest lithium ion battery, okay, like Tesla and Neons are there, okay, provides frequency control, grid balancing is there, saved millions in ancillary service cost, okay. China's pumped hydro, almost 120 gigawatt of capacity they are planning to build by 2030. Then leading deployment of battery-based energy storage. In US, California, they are almost trying to install 5 gigawatt. Okay, supports renewable penetration targets. So Europe's hydrogen storage, power to gas facilities in Germany and Netherlands, they are installing. So linking renewable electricity with gas-based infrastructure. So this is also a diagrammatic representation. Wind turbine can also be used to generate electricity, and it can be converted into hydrogen, electrolyzer, compressor, then hydrogen tank, then hydrogen pipeline, then fuel cell to generate the electricity again back, or this can be used to transport to the market, and it can be sold, or autonomous hydrogen based industries can be also operated. Definitely hydrogen is also used in lot of chemical plants also, like metal hydrates, they can be built. So other alternate options are also available. So then what are the different challenges? Okay, so technical challenges in grid scale energy storage, and what are the future directions that we will see now. So limited long duration storage solutions are there. Okay, only most of them are short duration. Okay, not suitable for long range. Okay, long duration. Then degradation of lithium ion batteries over time. So maintenance is there. Its life will be reduced. Multiple charging and discharging cycle. Efficiency of most of the grid scale like hydrogen storage, then compressed air based energy storage, that is very low. Similarly, economic challenges, high initial cost. Okay, this is one of the very important requirement. High upfront cost, need for clear market signals. Okay, capacity markets, ancillary services, environmental and social challenges are also there, like resources, mining, cobalt, lithium, all these things I have already mentioned previously. Then safety, fires, land use is there. Then long duration energy storage, greater than 10 hours, which is not that much available presently. So iron air based gravity storage, advanced flow batteries, these things are still under research and development. Hybrid system, like combination of one and more, okay, like battery or hydrogen, similarly compressed air or hydrogen. So that options can also be thought of. Okay, so these are all future direction. AI driven optimization can be also done. Policy should be also made properly, like incentives should be provided, renewable portfolio should be standardized, carbon pricing should be also managed. Okay, so in summary we can conclude that the grid scale energy storage is essential for reliable and renewable powered electricity systems. Okay, so definitely large scale energy storage is the need of the hour. Okay, to enhance the higher penetration of renewable sources, because to tackle the intermittency of the renewable, definitely grid scale energy storage will play a very vital role. The multiple technology exist, so each suit for specific users. Okay, some short term are there, some long term, sometimes is having bulk storage, sometimes some of them are grid supportive. Okay, so not suitable, all of them may not be suitable for all the different applications. So depending upon that one, we have to select any one of them. So what are the takeaways? So no one size fit all solution. Future will rely on technology mix. So combination of these grid scale energy storage we need to consider. Innovations in chemistry, efficiency, policy will decide the pace of the adoption. So finally we can say, as we move towards the net zero grids, net zero means zero carbon emissions, carbon dioxide emissions from the grid. Okay, energy storage will become the new backbone of the electricity. So definitely contributions of renewable sources and support provided by the energy storage will keep on increasing with each passage of the time. So this was the last slide. With this we will conclude the today's session. Thank you.